Hey everybody, so we are now going to start your final exam material. Hopefully you all did as well on your midterm as you wanted to. So from the sections 2.6 on through, I think we go through 3.9 in this class, all this material is what you're responsible for your final exam. We're going to begin today by talking about a new derivative rule that I did not want to put on the midterm because it's a little bit different, but it's a derivative rule called implicit differentiation. And essentially it's a little bit unique, it's a little different, so we're going to kind of work through what it is in this first section here in this video. So every derivative that you've taken so far has been written in the form either f of x equals something or y equals something, and you've been able to take the derivative pretty easily. But you actually don't have to have the derivative, you don't have to have the function in that order to take the derivative. So what I want to show you here is start off with an example. I'm going to teach you what implicit differentiation is by doing an example. It's going to make a lot more sense than me trying to put a bunch of mumbo jumbo math words up here. So here's what we're going to look at. If you've got 9x squared minus y squared equals 1. When you take a derivative implicitly, you don't move anything. You take the derivative exactly as you see it from left to right. Now there's a trick, and I'm going to get to that in a second. The derivative of 9x squared is 18x. The derivative of negative y squared is negative 2y. And stop. This is where it's different. Anytime you take the derivative of a y term, you have to add an implicit step, which is called dy dx. So you just stick it onto every y derivative you take. This is equal to the derivative of 1 is 0. And since dy dx represents the derivative, your job is to get the dy dx by itself by using algebra. So I'm going to move this term over to the right, which makes it 18x equals 2y times dy dx. And then if I divide both sides by 2y, those cancel, you end up with a 9x over y equals dy dx. And you may not believe it, but that is your answer. That is the derivative of this function. Now, obviously, with an implicit derivative, you have to make sure that you know that there are going to be y's involved. This y is what y would equal if you were to solve for it up here. Now, that's the new way we're going to do it. So after this problem, this is all we're going to do. But let me show you why this is the same thing. Normally, if you were given this function in the previous material, you would have to get that y by itself. So I would add y squared to both sides to have 9x squared equals 1 plus y squared. I would subtract the 1 over. So 9x squared minus 1 is y squared. And then taking the square root of both sides would say that the square root of 9x squared minus 1 is equal to y. This is something you could take the derivative of. You could say y is equal to, so rewrite your problem as 9x squared minus 1 to the 1/2 power. This is chain rule, so your derivative part's going to be over here. Y prime would equal 1/2 to the front. Leave the inside alone, drop the power down by 1 to the negative 1/2, and then taking the derivative of the inside is 18x. Well, if you take the 1/2 times the 18x, that gives you a 9x times 9x squared minus 1 to the negative 1/2. And while I didn't make you rewrite this stuff in the previous material, starting from here, we're going to be rewriting a lot more things. So if I were to put this back on the bottom, because I want the power to be positive, this would be 9x over 9x squared minus 1 to the 1/2. But if you notice, that now matches exactly the bottom part what your y was equal to. So I can say that this is equal to 9x over y, which is the same thing we found when we did the implicit derivative. Now this red stuff took a lot more work. The purple went really quick. So that's the idea. You don't have to rewrite anything to take the derivative implicitly. All right, so let's do some examples. Let's just do all implicit derivatives. That's all this section is going to be about. Find the derivative of x squared minus 4xy plus y squared equals 4. So starting from the left, remember, don't rearrange anything. The derivative of x squared is 2x. Now you have to pay attention. Since we're not rearranging anything, we have to think of the following. The negative 4x times the y as being a product rule. And remember, the product rule is going to be your fg prime plus gf prime, where f is negative 4x and g is going to be y. So what happens when we do that? Your f is negative 4x times the derivative of y, which is 1, but since you took the derivative of a y term, it's dy dx as well. All right, plus your g, which is y, times the derivative of f, which is negative 4. No extra term. The derivative of an x term is normal. Then you're going to add to this the derivative of y squared, which is 2y, times another dy dx, because you did a y derivative, equals the derivative of 4 is 0. I'm going to clean this up a little bit, so it looks like we can write this as 2x minus 4x dy dx minus 4y plus 2y dy dx equals 0. Now, since you've got multiple dy dx's, let me show you how we'll deal with that. First thing is I'm going to move everything that doesn't have a dy dx to the other side. So when I come down here, you have a negative 4x dy dx, and you've got the plus 2y dy dx. The other two terms, the 2x, and I'm going to box these or circle these in, the 2x and the negative 4y, I'm going to move to the other side of the equal sign to make this a negative 2x plus 4y. Now to turn both of these dy dx's into one dy dx, I'm going to factor out, because it's in common, which leaves me a negative 4x and a plus 2y left over. Oops. On the right-hand side, you still have the negative 2x plus 4y. And to get that dy dx by itself, you now just need to divide by everything that's inside that parentheses. So negative 4x. That cancels. Now, you need to get in the habit of simplifying this. While it's not required right now, it just makes it look a lot nicer. There's no letters in common of all four things, but everything has a 2 in common, so I'm going to divide everything by a 2 to make this a negative x plus 2y over a negative 2x plus y. That is your implicit derivative. Very good. So you can take the implicit derivative as long as you follow your same product rule, and we might see a quotient rule here in a second. As long as those rules still apply, you can do the implicit derivatives. Speak of the devil, here is an example of a quotient rule. So we are going to take x squared over x plus y equal to y squared plus 1, and we are going to find the derivative implicitly. So to start right off, if you start from left to right taking your derivatives, I already see that we have an f function divided by a g function. And when they're divided, that means you have to do the quotient rule. So that would be gf prime minus fg prime over g squared. When you apply the quotient rule of the left-hand side, this is going to end up being x plus y times the derivative of f, which is 2x, so nothing different yet, minus f, which is x squared, times the derivative of g. So the derivative of x is 1. The derivative of y, while it is 1, you have to also multiply that by a dy dx. So I'm just going to call this 1 plus dy dx over g squared. So that's the left-hand side. The right-hand side, the derivative of y squared is 2y dy dx plus, oops, nope, no plus, the derivative of 1 is 0, so that term's actually gone. Good. One less term to worry about. All right, so let's see. A little bit of cleaning up here to do. I'm going to actually do 2 steps in one. So what I'm going to do first is I'm going to multiply everything on both sides by x plus y all squared. I do that because I want to cancel that 1 off the bottom. So once that goes away, I just got to clean up the top, which makes this a 2x squared plus 2xy minus an x squared minus an x squared dy dx. This is now equal to, all right, so you've got a, I'm actually not going to simplify this. I thought about it, but I think it may be easier to leave alone. So I'm going to rearrange some things. I'm going to write this as 2y times x plus y squared times dy dx. Your job is still to get the dy dx's by themselves, so I'm going to actually move this term, because that's the only dy dx on this side, and this whole one term's dy dx. I'm going to move it over to this side to make it 2x squared plus 2xy minus x squared equals 2y times x plus y squared times dy dx plus an x squared dy dx. Now we're back to that same factoring technique. So you're going to have a 2x squared, the left-hand side won't change, plus 2xy minus x squared is equal to, if I factor the dy dx out, that's going to leave me with a 2y times x plus y squared plus an x squared. And then we're going to divide everything by what's inside this parenthesis. So the 2y times x plus y squared plus x squared all over 2y times x plus y squared plus x squared. And I don't see anything in common with anything. So while this cancels, and I could rewrite it a little bit nicer up here if I needed to, but as you can see from right here, this is your derivative. It's not pretty. A lot of these implicit derivatives are not going to be very pretty, but that's how it is. All right, so let's look at one that involves the chain rule here a little bit. So in this case, you have the cosine of xy is going to equal 1 plus sine of y. First thing you want to do is see if is there anything that looks weird. Well, that cosine of x times y is what's going to be a little bit different here. All right, so nothing to move around. We're going to start taking our derivative from left to right. So when you do the cosine of xy, that is going to be a chain rule because you have more than an x inside of your angle. So starting from the outside, the derivative of cosine is negative sine. You leave the inside alone, but then you have to multiply this by the derivative of xy because that is going to be a product rule. So the chain rule part does become a product. So you've got your f is x, your g is y. So you would do f times the derivative of y, which is dy dx, plus y times the derivative of x is 1. This is equal to, the derivative of 1 is 0. The derivative of sine of y, while normally it would just be cosine of y is not x, so you have to take the derivative of that. The derivative of y for chain rule is dy dx. All right, so cleaning this up a little bit, I'm going to take this negative sine function and I'm going to multiply it by both terms inside the parentheses. That's going to give me a negative x sine of xy dy dx. Oops, don't freeze, there we go. All right, minus a y sine of xy. Sorry for the bad handwriting, everybody. This is equal to the cosine of y dy dx. All right, got to get the dy dx's on the same side, so I'm going to take this entire term here and move it over to the right-hand side. That way I have a negative y sine of xy is equal to cosine of y dy dx. Then I'm going to add, let's see, x sine of xy dy dx. You'll see it a lot in the rest of this section. Factor out your dy dx. So while that doesn't change the left-hand side, if I factor a dy dx out of both of those terms, that leaves me with a cosine of y plus x sine of xy. Divide both sides by what's inside parentheses, brackets, whatever you choose to do. So that's cosine of y plus x sine of xy. Do that on both sides. A lot of writing you're probably seeing. These cancel, and now that your dy dx is by itself, once again, while it's not pretty, This is the derivative of your function. Negative y sine of xy divided by cosine of y plus x sine of xy. All right, now that we've gotten down the idea of implicit derivatives, well, welcome back tangent lines. So every time we learn a new derivative rule, we have done a tangent line, and this is no different. We're going to do two of these because these are a little different. I want you to use implicit differentiation to find an equation of the tangent line to the curve at the point. So we're going to do y sine of 2x equals x cosine of 2y. So first thing I'm going to do is I'm going to take the derivative. And what you'll notice on both sides of the equal sign, while you don't have to rearrange anything, both sides have a product, and therefore both sides do require the product rule. So let's do the product rule of both sides implicitly. On the left-hand side, I would take the y times the derivative of sine 2x, so that would be cosine of 2x times the derivative of 2x for chain rule is 2, plus sine of 2x times the derivative of y, which is dy dx. I just realized, make this look a little bit easier to follow. Let me put my angles in parentheses. Apologize for that. That's the left-hand side. This is now equal to, do the product rule again. You're going to take x times the derivative of cosine 2y is negative sine of 2y times the derivative of 2y, which is 2 dy dx, plus cosine of 2y times the derivative of x, which is just 1. Now, let's clean this up. I can write this as 2y cosine of 2x plus sine of 2x times dy dx. This is equal to negative 2x sine of 2y dy dx plus cosine of 2y. What I'm going to do different, though, is don't try to rearrange anything. There's a lot of stuff. And remember, we're doing a tangent line, so we've got to actually plug some numbers in. Normally, we would only plug the x in to get the slope of the tangent line, but since we have implicit, you've got to now plug in your x and your y to find these. So everywhere I see an x, I'm going to plug in pi over 2. Everywhere I see a y, I'm going to plug in pi over 4. So here we go. This is going to be 2 times pi over 4 times the cosine. Now I got to double this, so 2 times pi over 2 is pi, plus the sine, got to do it again, so sine of pi. Remember, dy dx is the only thing you won't know here, so just leave those alone. This equals negative 2 times pi over 2 times the sine of, if I double pi over 4, that's pi over 2 dy dx, plus the cosine of double pi over 4 again, and that's pi over 2. Now, if you've been learning your trig functions for the last couple weeks, you probably know some of this stuff is going to go away. For example, sine of pi is 0. So that whole term right there goes to 0, and so does the cosine of pi over 2. Those are both 0 values. Everything else is not 0, so we got to actually finish simplifying this. If you double pi over 4, that's pi over 2. Cosine of pi is equal to negative 1, so that part's done. This is equal to, if you negative double pi over 2, you get a negative pi. Sine of pi over 2 is 1 times dy dx. All right, so this is going to end up being negative pi over 2 equals negative pi dy dx. And if I divide both sides by negative pi, so if I divide the negative pi out of that, that comes out really nice. You get a very, very nice slope of 1/2. I know it's equal to dy dx, but remember that number is equal to dy dx evaluated at both points, at both values of the point. So this right here is your slope. Now that you know your slope and you have the x and y from the beginning, you can write the equation of your tangent line. So this will end up equaling y minus your y value equals the slope times x minus the x value. That is y minus pi over 4 equals 1/2 x minus pi over 4. And will you look at that? If you add pi over 4 to both sides. I did not mean for this to happen when I picked this problem out. If you add pi over 4 to both sides, it cancels on both sides, and you get a very nice answer for such an ugly problem. Your answer is y equals 1/2 x. That is the equation of the tangent line at this problem at that particular point. So it's a little bit more tedious, but you'll notice that I did not solve for dy dx until after I plugged the numbers in, just to make the arithmetic a little bit easier. And I'm going to do the exact same thing on the next one as well. All right, speaking of the next one, so the last problem for section 2.6 is I want you to use implicit differentiation to find an equation of the tangent line to the curve at the given point. And I picked out x squared plus y squared equals 2x squared plus 2y squared minus x all squared at the point 0, 1/2. So to make it look a little bit nicer, I gave you the picture, and this is actually a graph that if you have to go on into Cal 3, you will see this graph again, only in a different format. For now, you don't know enough to write this equation in the way that we want to see it in Cal 3. So for now, we have to do it the ugly way. That's fine. We can still do it implicitly. So let's do the exact same steps again. Step number 1, let's find the derivative from left to right. The good news is there's no product rule, but you do have a chain rule on the right-hand side. So let's see the derivative. Derivative of x squared is 2x. Y squared becomes 2y times dy dx. Here's the chain rule. Since this whole thing is being raised to the second power, you bring this 2 all the way to the front. You leave the inside alone. Drop the power down to the first, and then you have to take the derivative of the inside, which is part of the chain rule. That would be 4x plus 4y dy dx minus 1. And once again, that is really ugly, but don't try to rearrange anything. Since we're just looking for slope of a tangent line, I am now going to let x be 0, which is great, and I'm going to let y be 1/2 everywhere in this problem. So essentially, anything with an x, I don't have to worry about. So I'm going to cross a lot of things out here. This term goes away, this term goes away, this term goes away, and this term goes away. So you lost 4 terms without having to do anything. Now you got to worry about all the y's. So if all these y's were 1/2, that'll be 2 times 1/2 times dy dx equals 2, open parentheses, 2 times 1/2 squared. All right, that's all that's inside there. And then all of that multiplied by 4 times 1/2 dy dx minus 1. 2 times 1/2 just goes away, so you're left with a dy dx on the left equals 2 times 1/2 all squared is 1/4, and if you double 1/4, you get another 1/2 times 2 dy dx minus 1. Once again, half of 2 is 1, so that term, this term right here is not really there, it's just a 1. And then if I want to get the dy dx's by themselves, I would, let's actually write this out so you can see. This is dy dx equals 2 dy dx minus 1. It doesn't matter. I'm going to move the dy dx's to the left, so if I subtract the 2 over, you actually get a negative dy dx equals -1. And since both sides are just the negatives of what you want, you can divide both sides by a -1, and that's even a better slope. You get dy dx is 1, and remember that, since we plugged our x and y in, that is the slope of your tangent line. And even better, since 0, 1/2 is a y-intercept, you can jump straight to the form y equals mx plus b. So your final answer is y equals x plus 1/2. So if I were to visually draw this, it looks something like that. That is the equation of your tangent line at that particular point. Very good. So that ends section 2.6. Once again, not a very long section, but a very important section for something we're going to see in the next video when we start doing word problems. But before we get into all the implicit word problems, I'm going to look at a couple of easier word problems for you to kind of get you warmed up. So section 2.7 is next. This is the rates of change in the natural and social sciences. And you're going to notice if you look ahead in the notes before we start working these, there's not a lot of problems to work. But There is a couple important key concepts we're going to look at. Velocity, acceleration, and position play a big role in this section. So just kind of be aware. There's a lot of tedious things to do here. Not a lot of problems, just a lot of steps. So here we go. All right, so let's begin with problem number 1. So nothing new here. I'm just going to jump straight into the problem. We're going to work through this together. Now, I will say there are a couple problems in this section that might require a calculator, so just kind of keep that in mind. A particle moves according to a law of motion, S equals F of t for t greater than or equal to 0, where t is measured in seconds and S is in feet. So the big thing to notice there is that this all has to do with position functions, and t is time, and since we don't measure negative time, that's why all t values are only positive or 0. So question number 1 says, what is the velocity at time t? So remember from before the midterm, velocity is equal to the derivative of position. So if I just take the derivative here, that would be 3t squared minus 24t plus 36, and you're done. This is the answer to part A, and some of the problems will be a lot easier than others. What is the velocity after 3 seconds? Well, simply just take whatever number they give you on the homework and plug that into your derivative. That would be 3 times 3 squared minus 24 times 3 plus 36, which is equal to, let's see, if you need to use a calculator, that's fine. Let's see, that's 27 minus, what is 24 times 3? I'm having a brain fart this afternoon. Minus 72 plus 36. And let's see, that's going to be negative 9, and we're doing feet per second. So we have a negative velocity, and we're going to get into a lot more what that means here in just a second. All right, so first new thing, when is the particle at rest? The particle will be at rest when it has no velocity, so we want to know where is v of t equal to 0. So I'm going to take my velocity function, which is 3t squared minus 24t plus 36, and I'm going to set that equal to 0. I notice that all 3 terms have a 3 in common, so if I factor a 3 out, that would be t squared minus 8t plus 12 is equal to 0. The inside of those parentheses do factor. I believe it factors into t minus 6 and t minus 2. Setting what you can equal to 0, remember the 3 doesn't really matter here, so I'm going to say t minus 6 is 0 and t minus 2 is 0. So we get t equals 6 and t equals 2. So at 2 seconds and 6 seconds, the particle comes to rest, at least at that instantaneous moment. So my next question is, all right, when is the particle moving in the positive direction? Well, in that case, you are asking yourself, where is v of t greater than 0? So the way that I teach this may be a little bit different than maybe somebody you know has shown this to you before, or maybe you'll see it again. I do it with a number line, and I'm going to do a lot of number lines in this section, so just be ready. I'm going to take v of t and draw it on my number line. And since I care about where it's positive, I know it can't be positive where it's 0. So the 2 and the 6 that you found on the last part of the problem, I'm going to mark those on my number line. And then I'm going to cleverly just pick a few numbers that fall in between them. So something less than 2 is 0. Something between 2 and 6, I just picked 3. And anything bigger than 6 you can pick, I picked 7. Plug these into your velocity vec function. So that's the first answer we found. If you and you can use your calculator if you need to. If you plug 0 in, I don't care what the number is. I'll write it down, that way you can follow along. But if you plug 0 in, you're going to get 36. All we care about is that that's positive, because that's what it's asking. It's not asking what it is. It's just asking, is it positive? We already plugged 3 into velocity. That was part B. We got a negative 9, so I'll write that down again. That is negative. And then 7, you might have to use a calculator on, so I'll literally click on the number crunch here while I'm in my office. If I plug 7 into the velocity function, I got 15. That is a positive number. We care about these positive parts, and you have to write this answer in interval notation. Now be careful, don't say negative infinity to 2. Since time cannot be negative, we have to go from 0 to 2, union from 6 to infinity. Now I am inclusive of 0 because the 0 is included in my parameters at the very beginning. So I'm not done with this problem. That's the first part of it, but that is part A through D. All right, so now you want to find the total distance traveled during the first 8 seconds. All right, so if you want to find total distance, this is where it's a little bit different. If you were looking for displacement, one thing I've heard people tell me before is that, well, you would just do f of 8 minus f of 0. And that would be correct if you were doing, I'm going to abbreviate here, displacement. But since I want total distance, you have to do every set of parameters that you saw on that number line. So what we have to do here is we have to do f of 2 minus f of 0 to get the total distance traveled in the first 2 seconds. Then you have to add to that f of 6 minus f of 2, and you'll notice the absolute values are there because I need everything to be positive. I need the total distance traveled in the next 4 seconds from 2 to 6, and then plus I want to go f of 8 minus f of 6. Now these are getting plugged into the original function here, so make sure, I hope you wrote that down. If not, pause the video and backtrack a little bit because you got to plug these in here. So to save a little bit of time, so if we plug all these in, I apologize, something fell in my pocket. Let's see, I'm trying to remember what it is because I don't have it in front of me. I believe that it was going to equal, let's see, I believe s of t was equal to t cubed. I'm trying to remember what it factored into. So give me 1 second. Let me actually pull up what it was. That would help me a whole lot right now. So just kind of stall here, listen to me talk for a few seconds while I pull up. I didn't think ahead when I was pulling these problems up. So let's see, we are working in this section. It would just help me, it'd help a lot. I didn't realize that I would lose sight of what I was working on. There we go. So the original function was t cubed minus 12t squared plus 36t. See, I'm not always prepared 100%, so I didn't feel like stopping the video, so you get to listen to me jabber for a few minutes. We got to plug all of these numbers in. So I'm just going to use my calculator. So I'm going to plug 2 and all that stuff into here. So if you plug 2 into this, let's see, 8 minus, you should get 32. If you plug 0 in, you get 0. Plus, if you plug 6 in, that number's kind of big. So 6 cubed minus 12 times 36. Oops, wrong button. I am struggling on this afternoon, y'all. I do apologize. How about 6 cubed minus 12 times 36 plus 36 times 6? Oh, there we go. Actually, so you get 0 minus 32 plus, I did 8 really quick while I was doing both of them. So that's 32 minus 0. So if you take the absolute value of all of these, you actually get 32 plus 32 plus 32. That's a nice little coincidence there. And you get 96 feet. Very good. All right, so now you want to find the acceleration at time t and after 3 seconds. So for acceleration, we're going to take the derivative of the velocity vector that we just found. So in this case, we are going to say that a of t is equal to v prime of t, and hopefully you wrote v of t down on your previous example. So v of t is going to actually, I'm sorry, a of t is going to be 6t minus 24, and the 36 will go to 0. So that's your acceleration. Then you've got to find the acceleration after 3 seconds. So that would be 6 times 3 minus 24, which is negative 6 feet per second squared. So you've got to divide by time squared when you're doing acceleration. All right, so then part G, this is the big one. This is what we're going to do a lot of for the rest, especially the next couple of problems. When is the particle speeding up and when is it slowing down? So we already did half of this work. So if you go back to the previous slide, I'm just going to draw it again. We had 2, 6, and we found that these intervals were positive, negative, and positive. So this came from the velocity. I'm going to do the exact same thing for acceleration. All right. So for acceleration, I got to figure out what numbers to plot on here. So I need to take my acceleration function, which is 6t minus 24, set that equal to 0. So 6t equals 24, and t equals 4. So I'm going to plot the 4. You notice that I plotted the 4 between the 2 and the 6 to try to keep this, because we're going to have to play a little matching game in these two lines. So let's see, if I pick a number, let's say 0 and 5, we're going to plug those numbers into the acceleration function in the first purple box you see above it. 6 times 0 minus 24, I don't care what the number is, I just know it's negative. And then 6 times 5 minus 24, once again, don't care the number, it's positive. And what you're going to see me do, and this is something I do, and a lot of people don't do this, I put dotted lines starting at 0 all the way until my last number, which is 6. And you're asking yourself two questions. It's saying, when's it speeding up and when's it slowing down? Speeding up is when both the velocity and acceleration are the same. And slowing down, which I usually call SD, is when they are different. So your first interval will always start at 0 because that's when time starts. So let's start with speeding up, and we're going to do, and slowing down, we're going to do them one interval at a time. If this is 0, between 0 and 2, you have a positive velocity, but yet a negative acceleration. So they are different. So at the beginning of time, according to this math, you are actually slowing down to start off. So we're going to slow down from 0 to 2. From this 2 to this 4, you have a negative velocity and a negative acceleration. So you're going to end up speeding up. So 2 to 4. All right, so from 4 to 6, you're going to notice that it keeps flip-flopping. So then union, from 4 to 6, you have negative velocity but positive acceleration. So from 4 to 6, you are slowing down. And then from 6 to infinity, your velocity and your acceleration are both positive. So you're speeding up from 6 seconds until the end of time, which doesn't make much sense. But once again, this is just pure mathematical problems right now. So that's what we're looking at. But very good. All right, so where this can get a little tricky is, what if you're not given a function? What if instead you want to do the exact same thing I just showed you, only you have to do it with velocity functions? So in this case, for the velocity functions, if we're going to do two of these, if this is your velocity function, so don't even look at the second graph right now. This velocity function, can you tell me where it's speeding up and where it's slowing down? So remember, we need two different charts here. We're going to need our line chart with velocity, which we can already do here, because starting at from 0 to 2 seconds, you can tell from 0 to 2, your velocity is above the axis, so it's positive, and then from 2 to 3, so we're going to actually stop here at 3, it's negative. Where it's a little trickier is you got to do the exact same thing for acceleration, and this goes back to the graphing stuff we did with derivatives back in section 2.2. Remember that whenever you change from increasing to decreasing, that is where your positive and negative changes. So I'm actually going to plot the 1 right there. And since from 0 to 1 you are increasing, that means I have positive acceleration because that's the derivative. And then from 1 to 3 you are decreasing. So that would be negative acceleration because that is the derivative of velocity. And then you're back to my little dotted lines here. Let me change colors. So we're going to start at 0. We've got 1 at 1, 2, and we're going to stop at 3. From 0, so we got speeding up and slowing down. From 0 to 1, both graphs are the same. So you're actually speeding up from 0 to 1 second. From 1 to 2, velocity is positive, but acceleration is negative, so therefore they're backwards. So you're going to be slowing down from the 1 to 2 second mark. And from 2 to 3, both of your lines are negative, velocity and acceleration. So you will also be speeding up from 2 to 3. So that is your answer for just the first graph. That's just that part right there. So it's all about reading the velocity graph and then using your idea of derivatives in order to develop the acceleration graph. If that one didn't make much sense, let's do a second one to kind of show you. So based on this graph, we're going to go from 0 seconds to 4 seconds, and I'm going to start with velocity. If you are above the axis, that means your velocity is positive. So that starts at 0 above the axis all the way until you get to 3. So if we're starting at 0 and we'll say 3 is right here, all of this is positive. But from 3 to 4, you are below the t-axis, so therefore you have a negative velocity at that point. So here's where, once again, acceleration, you got to be able to read the graph. Think about derivatives. Find where does it change from increasing to decreasing and vice versa. So let me erase these 2 dots right here. Fill back in this. There we go. All right, so you change direction, let's see, from 0 to 1, you are decreasing. So from 0 to 1, we have negative acceleration. Decreasing means negative when the derivative comes around. From 1 to 2, you're increasing. So from 1 to 2, you get a positive acceleration. And from 2 to 4, you are decreasing. So all of that is negative. And once again, you are going to play the matching game. So I'm going to put a dotted line at every second here. And we're going to get our speeding up intervals and our slowing down intervals. So speeding up, actually it doesn't really matter. So from 0 to 1, you've got positive velocity and negative acceleration. So you're actually slowing down on the first interval. From 1 to 2, both line graphs are the same. So you're speeding up from 1 to 2. From 2 to 3, they're backwards again. So you're going to be slowing down. And then from 3 to 4, they're both negative, so you're both actually speeding up. So therefore, you've got 2 separate intervals of speeding up and 2 separate intervals of slowing down. So that's how you can find out where a particle is speeding up or slowing down based on the graph of the velocity function. All right, so to kind of get you ready for the next section, we're going to be looking at some word problems that don't work out very nicely, and we're going to have to use different ideas. So, for example, just to kind of get you warmed up, if I tell you a spherical balloon is being inflated, can you find the rate of increase of the surface area with respect to the radius r when r is 1 foot, 2 feet, 3 feet, and what conclusion can you make? So what we're going to see in the next video, especially in section 2.8, is that you're going to have some geometric formula. So surface area of a sphere, if you didn't know, is 4 pi r squared. And you're going to be asked to take the derivative with respect to a certain letter. In this case, that's r. That means that you're going to do an implicit derivative here. When you take the derivative of s, the derivative of s is normally 1. But since you're taking it with the respect to r, that is ds dr. It's kind of like when you did the implicit derivatives at the beginning of this video. You had to put the dy dx because you were taking the derivative of y with respect to x. So that's why this is here. Since the r you have is on the right-hand side, this 2 times this 4 pi is 8 pi r, but you don't need an implicit term because you took the derivative of the variable that you're doing respect to. So you're good there. Now the 1 doesn't do anything, so what you can say is that ds dr is equal to 8 pi r. And this essentially says mathematically that the derivative or the rate of change of the surface area with respect to the radius can always be found by the formula 8 pi r. Now, according to this, it just wants you to plug some numbers in. So we want to plug in r equals 1, r equals 2, and r equals 3. So that's not too hard. So find ds dr on all of these. ds dr, if you plug in 1, would be 8 pi. Now, what is the area? So that's going to end up being, it's going to be in feet per, and how fast are we going? It doesn't have time. It doesn't have time on here. Oh, not doing time. We're doing radius. So foot per. Oh, it doesn't even say. You know what? I'm not worried about it. So we'll get into more parameters later. So I'll just erase that. I didn't read enough information. So 8 pi is fine right now. So then we're going to do ds dr, and if you plug in 2, that's going to be 16 pi. And if you do ds dr, that's going to end up being 24 pi. Now, it's going to be a little bit more complicated in the next video when we get into section 2.8, but I kind of wanted to show you that we're going to start seeing a lot of these funny implicit terms with respect to geometric formulas, and we're going to review all of that in the coming videos. So the last problem that I have for this video does require 2 slides. So this is more of, like I say, if you have a calculator handy, you may want to have it because I'm going to be pulling some numbers out that I can't do in my head. So So A through C says if you can find the height in meters of a projectile shot vertically upward from a point 2 meters above ground level with an initial velocity of 24.5 meters per second, that is defined as h equals 2 plus 24.5 t minus 4.9 t squared. So just a couple of things to kind of get you used to doing word problems. Part A says find the velocity after 2 seconds. Well, if I know that position is h, I can say that the velocity of t is equal to h prime. So take the derivative of this. The 2 goes away. The 24.5t becomes 24.5, and then 2 times 4.9 makes this a 9.8t. To find the velocity after 2 seconds, I'm going to plug 2 into what I just found. That is 24.5 minus 9.8 times 2. So that's going to be 24.5, and I'm definitely using a calculator for everybody out there listening. That is going to end up being 6. Ooh, I can't math. I can't type in the calculator correct. Times, not plus. That's going to be equal to 4.9, and we're doing meters per second. So at 2 seconds, we are on the verge of going upwards. So question B asks, when does the projectile reach its maximum height? Well, it will reach its maximum, if we know it's being shot in the air, it's going to reach its maximum height when its velocity stops. So we got to figure out where is the velocity equal to 0. So I'm going to take the 24.5 minus the 9.8t, which is my velocity function, and set that equal to 0. If I move the 24.5 over, you'll have negative 9.8 equals negative 24.5. Oops, sorry, I forgot the t. And if you divide both sides by negative 9.8, you should get t is equal to 2.5 seconds. So while the velocity was 4.9 meters per second at 2 seconds, if we would have waited a half a second later, it would have actually hit its maximum height. So question C is, or part C, what is that maximum height? So you're now going to take this 2.5 seconds and plug it into your height function, because that will tell you how high the projectile was shot in the air. So that would be h of 2.5 is equal to 2 plus 24.5 times 2.5 minus 4.9 times 2.5 squared. And once again, just get your calculator out. Give me a few seconds to do this because I don't have these numbers. I can't do this part in my head. As good as I think I am, I'm not that good. So you end up getting a height of 32.625, and we're doing this in meters. So not very high, but that's okay. Never said it was a gun. It could have been a slingshot for all we know. But there you go. That is the maximum height of this projectile. Now there's 2 more parts to do on the next slide, so let's look at those. Part D says, when does it hit the ground? And part E says, what velocity does it have when it hits the ground? Okay, so the question is, when does it hit the ground? Well, it's going to hit the ground when you have a height of 0. So I need to make my height function equal 0, and that's when it will hit the ground. So 2 plus 24.5t minus 4.9t squared is equal 0. Now this does not factor. It's going to require you to go back and remember the quadratic formula that you learned in algebra. So we haven't reviewed that. So remember the negative b plus or minus the square root of b squared minus 4ac all over 2a, where in this case a is in front of the t squared, b is in front of the t, and c is your constant. If I plug those 3 numbers into this formula, that will give me when the time in which the particle hits the ground. So this is going to be negative 24.5 plus or minus the square root of 24.5 squared minus 4 times negative 4.9 times 2 all over 2 times a, which is negative 4.9. So now Give me a second because you're going to get two different answers here. So when you type all this in, you have to add the two things on top together and subtract them. So give yourself a minute or so. It's going to take me a minute or so. You should get two different t values when this happens. So let's see what those are. So give me a second. All right, so when I did the addition one, I actually got negative 0.08 seconds, and obviously that makes no sense. So you can't have negative time. So the plus one was not the one to do. Let's do the minus one really quick, so give me a second. So when I did the minus one, I actually got 5.08 seconds. So that is the only legitimate time when this particle could have hit the ground. So after you, or projectile. So once you shot it in the air, after a little over 5 seconds, it hit the ground. So the question is, what speed or what velocity did it have when it hit the ground? So you've now got to go back to the previous slide, and you should have had the velocity as 24.5 minus 9.8 t. You want to know what is the velocity at 5.08 seconds. All right, so we're going to do v of 5.08, which is 24.5 minus 9.8 times 5.08. And if you think about it, what should this velocity be besides the number? If you thought negative, you're correct, because if your projectile is going down towards the ground, you should have a negative velocity in this case. So let's see if we're right or not. I think we are. Yep, you get a velocity of negative 25.284 meters per second. So that makes sense that you are going in a downward direction when your when your projectile hits the ground. So that finishes up section 2.7. In the next video, I will warn you, there's two sections, 2.8 and 2.9. 2.8 is probably one of the harder sections we cover in this class, so come prepared. 2.9 is probably one of the easier sections we cover. So we kind of put them together. That way you don't feel so bad while watching all the video. So I'll see you next time.